Hello everyone. So in this video we will discuss CTQ number 3. Till the previous video we have covered two CTQs that are covered in three consecutive videos. There I have discussed about the concept of noise, offset, gain and many other concepts also. In this question, the concept of noise is only analyzed here, but whatever possible things I can cover I will discuss here. But basically, this question was given to analyze the input referred noise for two circuits. The concept here is to show you that what is the effect of cascode devices in the contribution of noise, also in the offset, which is not covered here. But you can see in the telescopic structure, which is covered in the 5 transistor OTS series, what is the contribution of cascode device in the offset. You will see that the cascode device actually affects uh, actually creates no effect of offset or noise at the output and hence at the input also. So what is the reason for that? We will see. This is the only main reason for this question, to understand the contribution of noise and offset of cascode device. So here we can see in this structure, this M2 is a cascode device. So the motivation of this question is to understand the concept of noise, to understand the concept of noise in cascode device, in cascode structure. Or so actually this M2 is your cascode device. We will see the contribution of noise due to every device at the output, but you can see that what is the effect of M2 transistor there. So I'll go through the consideration of noise of each and individual transistor, and I'll model that noise can be modeled for the transistor. Once I'll recap the concept which I already mentioned previously, but I'll say that any transistor can model in two ways. The noise of any transistor can be modeled in two ways. One thing is that if it is a noisy transistor, it can be modeled like a transistor which is noiseless with a current source parallel to this, which is nothing but a noise. So this is now noiseless, but this is a current or IN of this transistor M. So this transistor which was noisy previously is modeled like that, a parallel current source which is nothing but a noise current of this transistor, and now this transistor is noiseless. Other way of modeling is this transistor is now noiseless, but there is a voltage source on its gate which is nothing but we can give any polarity does not matter for the noise, because noise is a random quantity that I already covered. Okay, so this VNM is nothing but a noise voltage which can be modeled for a transistor. Now this transistor is nothing but a noiseless. Okay, so this way there is a modeling of transistor noise. Now we will see the contribution of each and every device in their noise contribution at output. Okay, so let us consider this circuit again on the next slide. Okay, so basically what is this? There is a current source which is nothing but a load, that is load current I naught, and this is your cascode device. So everyone knows how to calculate its gain. I am not going to that part. Later in some other CTQ I will cover this gain calculation for any structure which has the cascode in it. I already covered this thing in 5 transistor OTS series, where I discussed about the cascode device. So I'll mention there 5 transistor OTS series. You can see the complete analysis of gain for the cascode device, which is a telescopic structure. Okay, so okay, this is now considered that the current source can be implemented like this, which I already mentioned previously. So this is just a structure, and here we are considering that this current source is contributing to no noise. This current source is contributing to no noise, means it is an ideal current source. or can say golden current source, which is contributing to no noise. So okay, this is my structure where we are concerned about. So what we will do, I'll first consider the noise of this transistor M1. So this is my transistor M1, 2, 3, 4, and they are 1:1. So the current I note is copied there. Okay, so okay, this is the connection that I forgot. Okay, now we have to consider the each individual transistor's noise. So first I'll consider the noise of input device, that is your M1. Okay, so what we can see here, when we are doing the noise analysis, we can consider this thing to be shorted, and this is maybe ideal current source, or I can say, let's say it's internal resistor, that is R0. The noise of this transistor is considered. What is the effect of this noise as a output short circuit current due to the M1 transistor? Okay, so I'll call this as a drain to source. As I told you, direction does not matter that much, but if you have considered one direction, keep the direction throughout your analysis constant. Okay, so what you'll see that the noise coming from this transistors, so this I is coming out of it. What we can see here, this is a short circuit path, and this is a path has some resistance, that is a high impedance node. When we look upside, this M4, its drain is connected to this node, so it is a high impedance node. So current will not go this side because this is the short circuit side, so entire current is going to this side, or I can say entire current is coming from this side. So basically this current is coming from this side, so this entire this ISCN1 is nothing but this entire current noise of first transistor, that can be written as 4 kT gamma GM of this transistor 1 under root, or I can say the mean square value of this current noise is 4 kT gamma GM of first transistor. So this is the noise current that is completely flowing across a short circuit at the output. So and now we will consider the effect of transistors M3 and M4 noise. Okay, so if there is any noise associated with your transistor M3 and M4, what will be the effect at the output? We will see in the next slide. Okay, now if we have this transistor M3 and M4, we are considering their noise. I will consider this M2 at last, so that you can see the effect of cascade in the noise contribution. Okay, so this is my ISC noise due to 3. So what we will see from here, that no current is flowing downside, or I can see here, okay, yes, this is the short circuit path, so the entire current will go this side. This is a high impedance node. You can see at this node, because of there is a M2, drain of M2 is a high impedance node, so no current will flow this side, all current will go to the short circuit current. So what we will see, this is the structure, and if there is, this is also very high impedance R0, it is a, so whatever the current noise associated with this transistor I of N3, I will call I of N3, this complete is flowing upside, because this is a low impedance node. When we look at the upside, when we are looking up for this transistor, looking up, the impedance is nothing but 1 upon GM of the transistor, and this side impedance is large. So I can say this entire current which is going through, it is coming through this M3 only. This entire current is coming through M3 only, and it is copied here, which can be written as IN3 is completely coming here, and there is a short circuit part. So we can say that this complete IN3 is coming here, which can be written as 4kt gamma gm3. Okay, so it is under the root, and mean square value for this noise current can also be written as nothing but a out of root over gm3. Similarly, when we consider the noise of fourth transistor M4, we will see that complete contribution of noise current of this transistor is also coming to the output. Okay, so first we will short it. This is my R naught, which is very high, and this node is in the diode connected form. So this is my M2, and this is our, so the noise short circuit current due to this transistor 4 can be written like this. Okay, so what is this noise? The modeling of this noise can also be done again. It is nothing but I can write here source to drain, which is nothing but IN of 4 root. So we can see from here this current, because this current is passing through this, and here it is a short circuit path to come, and this is a high impedance node side. So complete current will flow through the short circuit path. I'll again say that direction does not matter that much. So whatever I have mentioned here, it is not that important for the noise quantity. It is nothing but IN4. So it is again, that is root 4 kt gamma gm of 4, or I can say the mean square value of this is 4 kt gamma gm 4. Okay, so this way we can see that total noise contributed due to these three devices is already fine. Now what is the point? Now main point is cascode device noise contribution. Cascode device noise contribution at output. Okay, so one more thing that I will say here, let consider the one point, consider gm3 equal to gm4. Okay, that will use this result at the end of this conclusion of this video. Okay, so now we'll consider the M2, or the noise of M2, so called cascode device. This is the now any cascode device is there. So we have this cascode device. For noise perspective, I will short it, and this noise is considered for this transistor like this, M2, and we have to see its effect at output. So this is your high impedance R0. So what we can see, this short circuit current ISCN due to 2. Okay, so what is this? This is actually IN2, and I consider it is flowing downward. What we can see, the upside is a low impedance node, and downside is a high impedance node. And one more thing that we can see, this side is a low impedance node, and these both are the high impedance nodes. So output short circuit means there is a low impedance side, and these both are the high impedance side. So now we have to see how this means current will split actually. So one easy way to understand any source current splittation, like how it will split, if there is some current I0, we can write it like this. This I0 middle point is grounded, and this is also I0. So any I0 can be splitted into the series of two I0 currents, where midpoint is grounded. As we can know, there is no current in this ground terminal, no current in ground terminal. This can be concluded from here. Okay, so I will split this current source like this only. So what is this? M2. So I am only drawing this M2 here, two nodes of M2, and we will split this current. Okay, so we will split this current like this. One source going to like this and ground, other current source current is coming this way. Okay, so I can write it like this. Okay, so this current source can be written like this same I naught or IN2 flowing out of this node is coming back to this node. So this is the ground, this is ground, there is no problem, the same concept is copying here. So what we can see, the lower side is a low impedance side, sorry, lower side is a high impedance side, and where we will see that how much current is actually copying. So actually this side is, so this node's downside is a high impedance side, this is the high impedance side, this is a low impedance side. So I can say that complete current is going up. So it can be said that complete current is going up. Okay, so the complete current is going up this way, no current is going this way. This noise current, complete current I can take, it is going up. And one more thing, now this upper side is your what, your upper side is high impedance side, this is also high impedance side. Now point is that where where this current is coming from, actually this is a high impedance side, no current, ideally we can understand no current will go there, this is also high impedance side, no current will go there, but whatever the current entering from the downside, it has to flow like this and it will flow out this. So overall we can see that the current which is entering at the source of M2 is coming out of the drain of M2, so it is cycling like this. So current entering into the source of M2 is coming out of drain of M2. So actually this noise current is just flowing in a circle across this M2 transistor. So it is contributing, this is a ISN2 out to 0. So from this concept we can understand the noise contribution at output due to all devices is what? M1 is contributing what? Directly 4 kT gamma GM1. This is output short circuit current. What is the M2? It is contributing to 0. What is M3? It is contributing to complete of its current GM3. What is the M4 contribution? It is a 4 kT gamma GM4. Okay, so this is short circuit current mean square value. So what is the total short circuit current mean square value at output? See, nothing but 4 kT gamma GM1 plus GM3 plus GM4. Okay, where we also considered initially that GM3 equal to GM4, I can write this short circuit noise current mean square value like 4 kT gamma GM1 plus 2 GM3 comma 4, they are same. Okay, so what is the input referred noise? Now I will write the input referred noise. So this is a total short circuit current, this is the short circuit noise current at output, short circuit noise current at output. Okay, so now if I want input referred noise, input referred noise, it will come what? Total output short circuit current mean square value divided by GM of the structure. This is the input referred noise that I will denote as a EN of, okay, I will call this mean square value of noise at input can be written as short circuit output current square, that is the mean square value divided by GM square. So what is this? 4 kT gamma GM1 plus 2gm 3 comma 4 divided by the gm of the structure is nothing but gm of 1 2 square. Sorry, there is a no 2, it is not a differential pair, it is actually a structure, so I am not writing here gm2. Okay, so what we can write exact expression for this, that is, what is the exact expression, that is our 4 kt gamma divided by gm of 1. So how we can optimize this noise? So for this structure, the noise can be optimized like optimization of noise. So always, what are the steps for noise optimization for any circuit? Optimization of noise for any circuit. For any circuit, what are the steps? The steps are, first we will calculate the output short circuit noise current. First output short circuit noise current, then gm of the structure. Third thing, refer this noise to input. Fourth point, look for dependencies on device parameters or DC operating points. So what we can see from here, the expression for our circuit is total input referred noise, that is, I will say input referred noise mean square value is nothing but 4 kt gamma divided by gm1 1 plus 2 gm 3 comma 4, because they are same, gm1. So how to reduce it? So we can directly see, increase the gm. We can directly see, first thing is increase the gm of input pair, which is called gm1. Second thing is reduce the gm of upper devices, means current mirrors. In general, we do this thing only for the input pair. For any structure, in general, we increase the gm of input pair. And how to increase the gm of input pair, that we will see. So how to improve noise specs, how to improve the noise parameters, how to improve the noise. Okay, how to improve the noise. So I am seeing that in the input referred noise term, what we are seeing that 4 kt gamma by gm1 1 plus 2 gm 3 4 by gm of 1. So what is the gm of 1? First thing, gm of first 1 can be written in many ways, 2id divided by v overdrive. Okay, so one thing is that if we want to increase the gm of 1, then what we can do, just increase the width. What we will do, it means directly, it means reducing overdrive voltage, because we can see that overdrive is what? Overdrive is nothing but VGS minus VTH. In the expression of current, when you see that this is nothing but Kn dash by 2 W by L VGS minus VTH, which we call it overdrive voltage square. So if we want to keep the current constant, if current is constant, then what can be done? If the current is constant, if this quantity is constant, and we have to increase the GM, then what you will do, we have to increase we have to sorry increase the GM1, so reduce the overdrive voltage. We have to reduce the overdrive voltage. So once the overdrive is reduced, you can see from this expression, if overdrive is reducing means W has to be increased so that the current can be constant. This is the one way. Second thing is that if we have the constant size, then what can we do? If there is a constant size, then it can be done like, if constant size is there and we are increasing the overdrive, then what you see, current will increase. To increase this, not okay, if we are reducing the GM, because we have to increase the GM anyway, so this is not a correct way to approach it. Okay, so this is the one way that I already mentioned. Now the second thing that we can think of is, what is the other expression for the GM? What is the other expression for the GM of one transistor? One expression is this: 2ID, one I can call 2ID mu n cox wi l of 1. Okay, so if I have to increase the GM of this first transistor, because I have to reduce the noise, what can we do? If the size is fixed, if constant WIL, then what we can do, we have to increase the current, so that GM1 can be increased, so that noise can be reduced. This is the other way. There are two ways. One way is this, where we can keep the current constant so that we can increase the size. Second, if size is constant, then we can increase the current so that GM can be increased, overall the noise can be reduced. The same such operations can be implemented for GM of 3 and 4, because these are also nothing but expression of ID 3/4 divided by overdrive of 3/4. One expression. Second expression also you can use it for 2 ID of 3/4 mu n, or mu p, I should say, mu p cox wil of 3/4. Okay, so there are the two expressions for the GM. So this way we can do some iterations to reduce the noise. And what other that apart from noise I can discuss for this circuit that I should see. Okay, so this is our circuit. Actually I asked about this noise spec of the circuit only. And what other I can think, any modification in this? Okay, if this cascode concept is extended to the PMOS, then also you have to apply the same thing. I mean to say, if this cascode concept is extended to upper side, means for the PMOS device also, means if I want to have some PMOS cascode as well, so if there is some structure like this, okay, if our structure is like this, VB of 2, and this is giving me VB of let's say 3, and this is nothing but okay, anyway, yeah, I can bias it like this. So there are two ways of its biasing. This is the one way of its biasing. This way we can bias it. Okay, so this is the one way of biasing. This is called wide swing cascode. Wide swing cascode current mirror as a load. So you can see about it, current mirror load. Okay, so this is also cascode device. My motive here it is that this is my M1, M2, that I call it M3, I call it M4. Okay, so what we see here, that two devices M2 and M3, these are the cascode devices, so they will contribute to 0, means cascode devices M2 and M3 will contribute no noise, will contribute no noise. So conclusion is that we can directly see at the cascode device. Just look at the cascode device in your structure, in this structure, and directly we can say no noise contribution, no contribution in noise and offset due to this cascode device. So this is the relax. There is no need of calculation of noise and offset if there are cascode devices present in your structure. This thing you can see in telescopic structure. For this you can have analysis. You can have the analysis of, for this concept to understand in detail, you can have the understanding of 5 transistor OTA, then its extended form, this telescopic op-amp, that also folded cascode structure, folded cascode op-amp. So here you can see the noise analysis, also the offset analysis, and you will see that the contribution due to the cascode devices means 0 or negligible. So this thing you can follow from one playlist from IIT Madras, that is by Aniruddha sir. Maybe spelling may not be correct, but Aniruddha sir, IIT Madras, analog IC design. If you want to see more about these concepts, analog IC design. In this course you will see that week 5, 6, 7 maybe, or I think 6, 7, 8, there is a complete discussion of telescopic op-amp and folded cascode op-amp. There you will see, you can see or you can figure out more about this noise and offset analysis. Rest 5 transistor OTA series, I also discussed this telescopic op-amp noise and offset concept where the cascode devices discussed in detail. So okay, this is the concept extended to the PMOS cascode. So later we can analyze many things here, but I will not cover all the things here. You can see the telescopic structure in the 5 transistor OTA series of my playlist. There all the concepts are detailed discussion, and the frequency analysis for any particular structure with the cascode device is also available in that series. So you can see also about the frequency analysis. Gain calculation is also discussed there. Okay, so this is enough for this particular question, how to improve this noise specs. That is a very important thing. It can be asked in interview, so you have to analyze the circuit very properly and with clear basics and fundamental concepts. If you do any jumble here and there, then obviously you cannot calculate the final calculation here. These instructions are so important because they can be asked anytime. Any random instructions can be asked where the offset, mismatches and noise analysis can be considered. So you have to first understand this concept clearly so that you can apply this concept in any random circuit. I'll take few more circuits in the noise and especially the offset calculation because they are recently asked questions. Previously last year I was asked with this mismatch question. My friend was also asked with this mismatch question. So you can see that how important these things are nowadays in analog IC design. Offset and noise is very important because these are some process which actually cause the error. One more concept, that is a linearity, I'll cover in some coming CTQs. The linearity is also very important, where we will see the second stage of op-amp, which is nothing but a class A structure, class AB structure, maybe the Monticelli biasing also. I'll talk about that. So as of now, this is enough for this particular CTQ. And so if you have any doubt remain, you can post in the LinkedIn or Telegram group, whatever, or in a YouTube comment section also. So this is enough for this video. Thank you.